All right, so let's get started. So what is Carbon Removal NYC? So what is this meetup here? I know some people have been here before. Some people probably have not. I know that a lot of new people have joined over the last couple of weeks or so, which is fantastic. I'm glad that people are still interested in meeting up even in these crazy COVID times. So Carbon Removal NYC is a meetup group for people who are interested in carbon removal, interested in learning about it, interested in doing it professionally, and just generally creating more of it existing and happening in the world because we need to remove a lot of carbon from the atmosphere. I'm getting some feedback from someone. Let's just mute. Yeah, thank you. Okay, and so Carbon Removal NYC hosts events for public audiences with speakers who are scientists and professionals studying and working on carbon removal. We've played with the format a little bit. This one seems to be the most interesting because there are some really interesting people who are working on studying and learning about carbon removal and trying to push the field forward. So we've played around with different things, but this one seems to work. And so we're gonna stick with this format for now. So we have speakers coming, and if anyone ever has any things that they would like to input into how we do the meetup, if you have any ideas, please let us know. This is definitely always a work in progress, and we would love to hear any other ideas. So our intention is to incubate conversations, relationships, initiatives, and businesses, and legislative action that support the reduction of carbon dioxide concentrations in the atmosphere. So in particular, we're talking about removing carbon from the atmosphere, actually reducing the overall concentrations. So what is carbon removal? So we've talked about this a little bit. I know that this is obvious for some people, but I know for some people this might be new. So carbon removal is the process of removing carbon dioxide from the atmosphere and keeping it out for decades, centuries, or millennia. So it is fundamentally different from cutting emissions. Cutting emissions or reducing emissions are very important to avoiding climate catastrophe. But at this point, with the amount of emissions that we already have in the atmosphere and with the fact that carbon dioxide stays in the atmosphere for so long, we need to remove carbon from the atmosphere to get to a safe place. So that's why I think a lot of us are interested in this topic now. So doing this could slow, limit, or even reverse climate change, but it is not a substitute for cutting greenhouse gas emissions. So one thing that we always like to make sure we reiterate here is that the carbon removal that we're talking about is not something that we're doing to continue emitting and offset that in some way. This is additional because we need to do it. So how does it work? So first, eliminate emissions. And second, this is how that would work. So when we look at going into the future and how we need to proceed to get to a safe level of warming, which is widely accepted to be 2 degrees Celsius, we need to cut emissions a lot. So we have up here, this is the cutting of emissions with conventional abatement technologies. And this is just a pretty simple graph that shows how we might get to staying on that 2 degrees C level there. This might be hard to read, so I'm gonna make this a little bit bigger. And so at a certain point, we see here that we really need to scale up carbon removal. So the technology is nascent in many ways, and it is growing though. So there are proven carbon removal technologies that already exist. And those are things that we need to scale up to these really large scales. So when we look at this blue area down here, this is getting into, we see this gigatons here on the left side of the graph. This is getting into some really large amounts of carbon removal. So what we're talking about doing is creating a carbon removal industry that is starting here very small and then ramping up. And that is in addition to cutting our emissions. So clearly we need to cut, mitigate, eliminate emissions. Up here, we need to do a lot of that. And that's all the good stuff that we're doing around efficiency and around nuclear power, any kind of renewable power, wind and solar, all that good stuff. We also need carbon removal. So this little blue spot right here, that's what we're talking about. So what does this actually look like? So we have some different examples here, and there's a lot here. If this is new to you, we can, I'm happy to talk at another time, but coastal blue carbon, this is the idea of absorbing carbon dioxide into marine parts of marine ecosystems. Accelerated chemical weathering in rocks. This is something that Caleb is going to talk to us about today with mineralization. Direct air capture uses these things that look a lot like fans, and they can actually capture carbon dioxide from the atmosphere, store it, and then take it and pump it somewhere where it can be stored for a very long time. And that often happens in this basalt rock down here. That's one very good way to store it. Another way is biomass energy with carbon capture and storage. And with that, we burn waste materials of biomass and we capture the CO2 from that. And so when that is done properly on a full life cycle basis and the full cycle of the whole process, it can be carbon negative, and it can be done improperly, in which case it wouldn't be carbon negative. For example, if we're cutting down old growth forest or something like that and then burning it, it's not a very good plan, but that can also be carbon negative. Afforestation and reforestation, trees remove carbon dioxide from the atmosphere. That is totally viable, and also there are some challenges there as well, because trees don't live as long as we need the carbon to be removed from the atmosphere. And there's a lot of complexity in there, but the really basic form of it is that trees are good, but they have a lifespan, and we need to remove a lot of carbon dioxide very permanently, because of the carbon that we have in the atmosphere comes from deep in the ground. It's in what's called the geocycle, and we have the biosphere, which is cycling carbon dioxide through trees in their lifespan, and it's kind of a different scale. So soil carbon also is very similar in terms of its impact, but it's stored in the soil. So those are some different types of carbon removal. If you want to learn more and you're new to it, there's some resources here, and you can find this page right here by going to intro.carbonremoval.nyc, and you can get right here, and these are all links, and that is that. So I'll put some housekeeping in the COVID era here at the end, which I mentioned at the beginning, but if you have questions while we're speaking, and I saw one come in, so I'm gonna see if there's a question that someone asked. If you have questions, then I will answer them. Oh, Zach had to jump. Okay, cool. All right. So does anyone have any questions now after the initial intro?
Yeah, I do. Hi, it's Peter Castellano.
Hey.
Quick question. After the last meeting, I was using the other platform for a while to talk to you guys. I forget the name of it.
Slack?
No, it was another one.
Oh, Discord?
Discord, yeah. So should I use Discord or the Slack? What's better?
Yeah, so we have a Slack set up, and if anyone wants to join, you can go to carbonremoval.nyc, and there's a link on the meetup page to join the Slack group, and that's for this group here. There's also a Discord that is for the Open Air Collective, which is another group, and they're working on advocacy for policy and R&D for carbon removal, for direct air capture in particular.
Got it.
And they are on the Discord. So I don't think we have anyone from Open Air except for me, and Lisa's here. Yeah, and Carmel. And Charles is in there too. So yeah, we do have some Open Air Collective people here.
Okay.
Yeah. Does anyone else have any questions? All right. So now we can talk to an actual scientist, and Caleb, you can correct me if anything I said was wrong.
No, everything seemed good so far. Yeah, so let me get my screen shared here. Let's see. Here we go. Is it working? Can
Yeah,
you see my screen?
Yes.
yeah.
Great. All right, everyone. Hi. As Peter said, my name's Caleb Woodall, and it's a pleasure to be here today. I see some familiar faces and others. It's great to meet you. I am a grad student at Worcester Polytechnic Institute under Jennifer Wilcox. She gave that TED talk that was listed on one of the resources here, but I'm here to talk about carbon mineralization and steps I'm taking and we're taking as a group to help its deployment to, as a solution for climate mitigation. All right, here we go. So the outline for this presentation is I'm going to first talk about the overarching problem of climate change that Peter already kind of went over, and then describe carbon mineralization as a pathway to mitigate these climate change problems. And then two things that I've been interested in that could help to deploy carbon mineralization and advance its deployment. And that includes the utilization of the mineralization products, and then a tool I recently developed for a techno-economic analysis of mineralization processes. So first off, once you start looking at our anthropogenic climate emissions, they're distributed in 5 main sectors. And in the US, the biggest one of those is the transportation sector. It's about 29% of all of our emissions. And the other ones are shown here that put the CO2 molecules to scale. And so once we're trying to find ways to mitigate these emissions, the first more well-known method would be to input renewable energy. And if we got like our entire electric sector renewable energy, we're working on that. It's not really quite there just yet, but even if we did that, we still have these emissions from say like jet fuel in agriculture, and then also in industry, chemical reactions that are inherent in the production of say like steel or cement. They are still producing CO2 that wouldn't be replaced with renewable energy. So a good way to mitigate that would be point source capture. Capturing CO2 at concentrated flue gases. At a cement kiln, you could get up to 30% CO2 in the flue gas streams. And the reason I'm talking about this purity is just because the more concentrated the CO2 is in your stream, the less thermodynamic work you have to do to capture that CO2. If you're capturing at a natural gas power plant, you're about 14% CO2. Coal power plants around 8%. But yeah, so we would want to do point source at the concentrated and large sources to minimize that work that we have to do to capture the CO2. But there's still going to be CO2 from smaller sources where it's not cost effective to do point source capture, or just places that are not concentrated. So there we employ direct air capture or carbon removal technologies or negative emissions technologies. And here's a plot, a figure that was just shown. And so I won't spend too much time going through it, but basically, again, you have your conventional abatement technologies that includes renewable energy and also point source capture. But then we have our negative emissions technologies that are removing carbon from the atmosphere, and that would include the direct air capture, those big fan modules that was shown. And something that both of these have in common is a necessity for stable storage of CO2. You capture and create this concentrated CO2 stream now, but now what do you do with it? And so that's where carbon mineralization will come in. Something to keep in mind while we're talking about this is, again, the scale of gigatons of CO2. That's 1 billion tons. That's, so we need to, and again, by like mid-century, we're wanting to, or by the end of the century, we should be removing like 10 to 20 gigatons of CO2 per year is the goal. So we're looking for solutions that are scalable to that gigaton scale. So could carbon mineralization fit that need? So what carbon mineralization is it's based on the fact that certain minerals naturally carbonate with the CO2 from the CO2 from the atmosphere on geologic timescales of millennia. And someone 30 years ago, Seifritz came up with or presented the idea that maybe we should be doing this intentionally to capture carbon dioxide. Of course, you'd have to be accelerating this reaction to industrial timescales of maybe hours to days rather than thousands of years. So what we need to do that is be getting alkalinity sources, which contain magnesium and calcium, and react them with CO2 to form carbonate minerals, as shown in this kind of simple reaction example here. So where would we get this alkalinity? First off, you have industrial alkalinity sources that are produced in varying quantities at different locations. I have some acronyms here. This is cement kiln dust at cement plants. Air pollution control residue is found at municipal solid waste incineration plants. Brines are from desalination plants. Anyway, with the exception of these liquid brines, all of these are solid particles that are already available at really small particle sizes, around 100 microns. And so, you don't have to do any extra milling to get them to your optimal particle size to have a good reactive surface area. They're also annually produced at, you see the scale of, millions of tons per year. And some of them are already available in stockpiled quantities that, they're just sitting there at a certain maybe coal plant or steel plant. And some of them even have like heavy metals or other hazardous nature that whenever you carbonate them, you actually neutralize that hazard. So this becomes, mineralization becomes both a carbon management and a waste management system in this case. And if you look at the future, these green bars represent generally expected to increase in production in the future, and red is generally decrease. But overall, a lot of these are expected to possibly be increasing in the coming years. And overall industrial alkalinity sources present a low-hanging fruit for mineralization feedstock. And alternatively, you have mine sources where you're looking at ultramafic, mostly all silicate rocks, which are available on the hundreds of millions to hundreds of billions of tons available. So again, this is that gigaton scale that we're looking for. This would require mining and size reduction of the rocks, which can be around maybe $10 per ton of rock. And on this note, you also have like whenever operations are mining for like diamonds or nickel, copper, you're mining for the desired commodity, but you also are digging up a bunch of other rocks that you don't want. And these are processed and left in stockpiles called tailings that also contain alkalinity and could be another low-hanging fruit. But anyway, whenever you're looking at these minerals, when trying to figure out how much CO2 could be captured per ton of rock, it's a function of the distribution of the alkaline cation in the structure, where this hydroxide is the simplest and can store the most CO2. However, you're not going to find as much brucite in the ground as you are going to be able to find a northite. Anyway, this would be like one of the more ideal minerals to get. And as the minerals become more complex, it's more difficult to capture the CO2. It's more restrictive to get access to alkaline cations. Yeah, and if I show you this next slide, kind of what I was just hitting on is the lattice structures in these different minerals, where this lizardite on the last slide is in the serpentine group of phyllosilicates. And so for example, these are in a sheet structure, and they have weaker bonds that are more easy to break apart and extract the alkalinity and carbonate it. Whereas this anorthite, you see here, this is a tectosilicate, and it's in a 3D framework. Basically, if you think of just like Legos staggered on top of each other, and it's much more difficult to break apart. And so this typically, like the pelagioclast feldspar typically isn't considered for mineralization because of this more restrictive lattice structure. However, this is something that I'm kind of looking into with my research, is because this feldspar represents about 40% of the Earth's crust. It's the most abundant in Earth's crust. So, if we are able to find a way to make it efficient with mineralization, then that would greatly increase the potential feedstock for mineralization. And this is a quick look at a map that one of my lab mates, Elaine, made, where this shows all of the alkalinity sources in the US. And as you can see, there's a good amount of opportunities throughout the US. However, as I may have mentioned with the industrial byproducts, they are distributed among various sites. So the goal, a trick is to try to find or co-locate, some multiple areas or areas of multiple production sites to try to, increase the scale of some kind of mineralization plant that you would be wanting to develop. So how do we perform mineralization? There's a couple of different general reaction schemes that are in the literature, and one of them is direct mineralization, where you're directly reacting the mineral with CO2. And this is good if you have a feedstock that is homogeneous. It doesn't have other elements, maybe like iron or aluminum, that would decrease the purity of your final product. So for example, maybe if you have magnesium oxide, which is a really easy example, and if you just react that directly with CO2, you can get your magnesium carbonate. And again, if you don't have a complicated feedstock, then this product purity and decrease in the full reaction extent might not matter. But if you have something like olivine, or something like a northite, which I showed earlier with like calcium and aluminum silicate, then you would want to find a way to extract that magnesium cation first into a more reactive form, and then react it with CO2. So in this case, for example, maybe if you react it with ammonium salt, then through an extraction step, and then once it gets into aqueous solution, you're going to have magnesium, more magnesium cations in solution that are available to react with CO2 and then form your magnesium carbonates. And again, this in this case, it would increase our product purity and reaction extent, but add extra steps and increase costs that might need to be compensated for later in the process, which I can get to later. So there's multiple ways, multiple methods to go about alkalinity extraction, and without going into all of these, the main thing to take away from is that there's multiple methods that apply better or worse to different types of minerals. However, they all are going to be adding economic and energetic costs. And again, you need to compensate for that later in the process. If you're looking at the challenges of the carbonation step, first off, you're doing carbonation step in aqueous solution typically. So the CO2 diffusion, dissolution into the water is governed by Henry's law, which is inversely proportional to temperature. So you don't want to have a high temperature carbonation step. But the way to increase the diffusion into water is just by increasing the CO2 pressure. Afterwards, you'll be, another problem is if the carbonation rate is faster than the rate that the product is diffusing from the main reactant particle, you could create a passivating layer. But employing good mixing would help to overcome this. Of course, that might add capital cost. And then if you're looking at the magnesium cation relative to the calcium cation, it has about 3/4 the ionic radius that calcium has, while they both have the same charge. So this higher charge to radius ratio promotes more interaction with water in solution. And that overall results in these hydrated carbonates forming. And these hydrated carbonates are heavier than the anhydrous form. Hydromagnesite is less efficient with its use of the magnesium cations, and they both are containing water. So that means you're losing water in the process, and you have to keep adding water just as another process expense. So magnesite would be the preferred form. However, you can need pressures of up to 100 bar of CO2 to be able to selectively precipitate magnesite rather than these hydrated carbonates in absence of other crystallization techniques. So again, this might be adding costs. So overall, if you're looking at a research agenda for mineralization, we want to be looking for ways to intensify the process, maybe by integrating energy. The carbonation step is exothermic, meaning that it releases heat. So if we could use that heat in the initial step of the process, that could save energy. Feed exploration, again, like the feedstock that I'm looking at, is trying to get it to where we can use feldspar. That would increase the potential, or just increase the overall potential impact of mineralization as a climate mitigation technology. And then just problems with scaling up the process and increasing efficiency. Now, another way to improve economics of all these points that I mentioned of where costs are increased would be to sell the products and compensate for that increased cost. And that comes to the second part of this talk, where why would we want to do carbon utilization? Again, extraction methods come with costs. Also, if we could be creating high quality products that are appreciated in the market, then we could be creating a demand for these carbonated products and encouraging more carbon sequestration. Also, if we're penetrating markets that their conventional products produce a lot of CO2, and now our products contain CO2, then that could further increase the impact of this technology. Also, with US Federal Tax Code 45Q, beneficial reuse of CO2 is incentivized with $35 per ton if you're at the scale of 25 to 500,000 tons of CO2 per year. So that's another reason to go for carbon utilization. So right now there's carbonates from the ground. However, a lot of these, shown in red, end up resulting in CO2 being re-emitted one way or the other. But the largest market here is the construction market. And again, we're looking for that gigaton scale. Portland cement is used at 4 gigatons per year. And it's actually very carbon intensive. It used to be about a ton of CO2 was emitted for every ton of Portland cement. Energy efficiency has improved that to a little less than a ton now. But Also aggregates for concrete mixtures are have a very high market volume. However, they are relatively inexpensive. So what we can see from this full figure and from this look at the construction market is that our mineralization products are going to need to be possessing characteristics that are superior to, like, say, these cheap aggregates to make up for the cost, or present new end uses that aren't shown here yet. So there's actually already some commercial endeavors that are using carbon mineralization, and so I divided those into two groups, one of which are basically taking CO2 and reacting it with some of that industrial waste to produce a carbonate aggregate, and then put that in a normal concrete mixture. Other ones are making a normal concrete mixture with Portland cement, but they inject CO2 into the mixture for the curing process, and this results in a stronger concrete product. Other companies are just performing mineralization with different types of wastes or alkaline sources to produce alternate building materials. So here is a table with a lot of numbers that the main thing to take away from here is looking at the markets that we could be breaking into with the mineralization products and the CO2 that's normally emitted by these products. Cement and concrete is kind of the same thing here. I'm just showing it in different lights. If you're trying to make an alternate cement versus just an alternate, if you're making an alternate cement that's used in conventional concrete, or just making a new, like, concrete brick altogether. Anyhow, something to take away from here is that magnesium is limited. Magnesium carbonates are limited in current markets where there's not very large markets available for them. You see a high market value for magnesite, just the magnesium carbonate. However, that's like for refractory metals that end up releasing the CO2, so that's not necessarily the purpose that we'd want to be selling our magnesite for. However, if you I did analysis on the potential to overall avoid CO2 from both the CO2 that's captured within the products plus the CO2 further avoided by replacing conventional concrete, for example. And that's what sorry, got out of order. The CO2 capacity is the amount of CO2 that's entrained in the products. And then this, on top of this, is added to the last column to the amount that would be replaced by, like, replacing normal concrete. And overall, I took a maximum value here of the CO2 that could be avoided if, all of the feed was used or all of the product market was met with these company processes. And this adds up to a little over 3 gigatons of CO2. Now, this is a maximum value. However, as I said, there's much more silicate minerals than is allowed for by, like, the magnesite market right now. So if that were to increase, that could, greatly increase this 14 value. And also, as I mentioned, some of these solid wastes are expected to be increasing in the coming years. And, so basically it could be approaching this maximum, we could be approaching this maximum value potentially in the coming years. So now to talk about the third part of this talk, and that's this techno-economic analysis tool that I recently developed. And so the reason of why we were kind of commissioned to make this by is Prime Energy Coalition. And you have researchers that have new mineralization processes and technology that are wanting funding. And they have all these claims about their process that they're telling investors, and then the investors have the funding, but they're not exactly sure which process is good and whether the process is actually practical because they're not as well versed in the mineralization realm. So this TEA tool is kind of made to bridge that gap. And you know, it was not a simple thing to produce just because of the high variability and like the three aspects of mineralization, which is the different feed that you can obtain, and then whatever process you're going to do to carbonate that feed, and then whatever product you're trying to make. So the approach I took here was to take a general multi-step process and allow the user, this is an Excel-based tool, and allow the user to activate or deactivate steps according to what the process under evaluation is. And then evaluate the techno-economics of this by accounting for all the material and energy inputs for the system, and then the revenue generated by whatever product you say you're going to produce, and then account for the capital expenses. Now, because with 45Q being, you know, a main factor of 45Q is the scale of CO2 that you're capturing, that we wanted that to be the more important parameter in this model. So I wound up doing a bottom-up mass balance, and what I mean by that is your main input is the amount of CO2 that's going to be sequestered by the process, and then after that I calculate the rest of the feed and other reactants required. So just as an example, like normally you might know that you have like 10 tons of lizardite, and that's like 26% magnesium. And if you have a perfect mineralization process that's going to get all of the magnesium out, then that would result in 2.6 tons of magnesium cations available in this aqueous carbonation solution. Now, just based on mass ratios, that would allow you to be capturing 4.76 tons of CO2. And again, this is at 100% efficiency, which of course is not practical. But and then again, based on mass balances, that would allow you to produce 9 tons of magnesium carbonate. But with this bottom-up approach, instead, you know, we want to define the amount of CO2 that's going to be captured by the process, and with that, use these same mass ratios that were available here, and to calculate the amount of magnesium carbonate that would produce, but then go backwards and say, okay, this is if I'm going to capture 10 tons of CO2 here, that means that 5.5 tons need to be available after the extraction, and then that overall means that I'm going to need 21 tons of magnesium lizardite. And this would apply, this is a kind of a sanity check for a process that say, you know, you're trying to get 25,000 tons of CO2, but they say that they're using, you know, some, you know, maybe air pollution control residue, which if you remember in that sources slide is very small. You might not be able to get 25,000 tons of CO2 if it requires, you know, maybe 70,000 tons of air pollution control residue, if that's not physically possible, as an example. So this is what the main control panel in the model looks like, and it employs a lot of like drop down lists like here to be able to pick different feedstock that you might be interested in evaluating. And right at the beginning is where you define the amount of CO2 captured per year. And just to run through a very quick example, I allow there to be 2 processes so that you can compare you know, changes in a process and how that affects the final costs. So if I mentioned the particle size of wanting about 100 microns optimally, but if you have this 25,000 microns, which is about an inch in diameter, then it would tell you that we're going to need to use a mill. So anyway, what you would scroll down to see is the control panel for every step in the process, and you can activate and deactivate it with these like yes or no. And I'm not going to go through this whole thing, but if you look at the this feed preparation step for this process one, I would want to tell it that we're going to use a mill and we need to get it down to 100 microns. And one last thing before looking at the outputs is the efficiency. And this would come into play as this bottom-up mass balance that I showed you, where it was all perfect, but then it now uses these extraction and dissolution efficiencies. And this avoids having to use complicated kinetic parameters that would require a whole lot of data mining that I simply didn't have the time or bandwidth to do. And this gives rough enough estimation for good evaluation of processes. And these type of efficiency numbers are pretty standard in the literature to be reported of processes that are being developed. So overall, now just to look at what this model is doing is it will be outputting yes, the main input variable is the mass of CO2. So like here at the very beginning, you're putting in the mass of CO2 that's captured per year. Yeah. So yeah, so the main output of this model is going to be showing you, as we defined at the beginning, we're putting 25,000 tons of CO2 into carbonate minerals. However, this is going to result in 2,000 tons being emitted by the process for a net 22,000 tons removed, or I shouldn't say removed unless, depending on the source of the CO2, but this is the amount of CO2 that's net put into carbonate minerals. And then showing the process economics with the capital, where I calculated capital and operating expense based on the value of the product that I defined at the beginning. This ends up being a negative value because you're profiting. And you'll see that in a second, but it lays out the capital expenses of the full process of each step. And the only difference between these two processes is the fact that we had to use a mill to decrease the particle size. But yeah, this allows you to see where the most expensive capital equipment is, and that is for this process, we're using a fired heater. And then you can look at operating expenses and just see where the layout of all the expenses from all of the materials used and the energy. And if we look at the energy costs, comparing these two processes where I decided to use milling for my process, size reduction is going to have an impact on your energy, but it's not a huge impact whenever you're just considering the amount of energy required. However, electric energy is more costly than thermal energy for these processes, so it has a higher impact on the overall energetic expenses of the process, and also with the emissions of the process. And again, this is just comparing the electric and the thermal energy used by this process. Anyway, also the model will also generate cost distribution for capital expense, and the only difference here is the fact that I used a mill, material expenses, and yeah, just as an example showing these. Also a cost sensitivity, so you can kind of evaluate at the point where these lines cross the x-axis the minimum or maximum value you need for your final process to be profitable. Looking at the feed cost, if you have to pay more than $50 per ton of the feed, then you won't be able to profit with this process. Or I defined that the product would be worth $80 per ton, but this is showing that it could have been worth 20 at the settings that I selected. Anyhow, this is just showing you an example of how it can be done. And for the future, what we're doing to work on this, my colleague also made a similar model for direct air capture. But now we're going to be working on making this an open source using Python. So it's much more interactive, and it's not this like blocky user interface that Excel has. And it's going to be a lot more easy to interact with. And with that, I want to be putting like location-based feed data and mapping to have more of a sanity check on what alkalinity is available in what location, and also just kinetics with the crystallization and also dissolution. But yeah, anyhow, that would be the end of my talk, and love to hear any questions. Thanks.
Fantastic. Thanks so much, Caleb. Yeah, we can clap quietly without blowing anyone's speakers out. That was really, really great. There's a lot of really interesting things in there. I know we might have some questions. I want to turn it over if anyone has questions, and I wrote down a couple myself.
Yeah, are we still putting them in the chat, or?
No, we can go ahead and just say them out.
Okay. Caleb, yeah, I was wondering if you could talk a little bit more about what the end products are of doing this process. I wasn't clear on like what aggregate is exactly, what comes out of this process physically?
So what you'd be producing is, well, yeah, so I mean, physically you're making different carbonate products, where that be kind of like what I said, you have basic like calcium or magnesium carbonates, or with magnesium, it could be like hydrated carbonates. And then, so construction aggregates, the common construction aggregates that are used are just limestone, which is just calcium carbonate, or dolomite. So these carbonate products could be used as aggregates, just as that. Or if you're wanting to make the cementitious products, then it requires a little extra finishing, either by like mixing these carbonates with water and putting them in cementitious mixtures. And I have to admit, I'm not as good as explaining how you make these other cementitious mixtures that the companies are doing, partly because it's not super well, they're not putting out their secrets super well. But yeah.
That's okay. That definitely answers my
your
question. Yeah, it does.
Yeah.
I read this A World in a Grain a couple of years ago. It's about the worldwide shortage of sand because of it going into Portland cement. And apparently the core deal on that shortage is that ocean sand is rolled around, so it's round and it's no good for building because it doesn't like grab on. Whereas the now rare mined sand has like angles on it, so it can grab in the cement. So if you could figure out a way to have your products in terms of that shape be a sand replacement, and I know that's not the carbonate part of Portland cement, but if you could figure out a way to have it replace the sand, that's now apparently a rare product. And I wondered if you had any thoughts about that.
Yeah, I've read about a process where they're actually trying to just using that. I could go in two directions with that. That I read about some people trying to lay out like olivine, for instance, with the issue that I said of like expenses due to having to mill it and reduce the particle size. Well, instead they just put kind of relatively larger particles on the coast and allow the ocean to come over and like basically with a wave energy decrease those particle sizes and then allow it to draw down CO2 from the atmosphere. So that's interesting. And something also that I've personally at least wondered about is, with all these silicates that you're gonna have to be using for feedstock, you're producing a lot of silica as a byproduct from this. So you know, that's something that's like been in the back of my mind of whether you could be using that as maybe a construction sand, but it's not something I've had the time to look as much
And
into
it seems
if
like
that's
the
possible.
key to that is the round as opposed to angular shape, and the
Yeah.
shape of building.
Yeah, Caleb, the beach method you were talking about is the one that I think I am most familiar with, or like at least I've heard about before. But it sounds like you're talking about doing this possibly in some type of a plant. Is that correct?
Like the methods that I was talking about in the process that like in the presentation, yeah, I've generally considered it more being in a plant, but yeah, what I said as the example with the ocean, yeah, that could be done. Yeah, like laying out on the ocean shore. And there's a lot of just thoughts on what's the best way to be doing this now. Like, is it good to be trying to do the mineralization and the utilization and making products, or is it overall just cheaper to be laying the stuff out on the ground and just let it take CO2 from the atmosphere? I think
Sure.
both would be useful,
Yeah.
especially these industrial byproducts that are near concentrated CO2 sources already.
Well, it sounds like that you could control it better if it was in a plant. I mean, just from what you said in your presentation.
Yes.
Yeah.
For reference, the Olivine Beach idea, that's Project Vesta. I've done some research on the work before and studied carbon mineralization a little bit. They estimated that with their method, you know, you could hit a ton of CO2 removed at like $8.40 or so. So it's a pretty interesting concept. But I think the point about it being less controlled and that you're creating olivine beaches, so you have some risk of, say, industrial mine waste in the olivine tailings leaking into the ocean. Like that's a possibility. Whereas a plant, you can have a bit more control over that. So quick question. I joined a little bit late because I was in the middle of the class. And sorry if you can hear the applause outside. So maybe you mentioned this in the very beginning when I wasn't in the session, but could you please discuss what you think is the balance between using saline aquifer storage versus mineralization? Is it just a matter of what's available? Because both are fairly abundant actually very abundant as I understand, but you have more saline storage in the US, but perhaps more olivine or mineralization potential in Algeria or Italy or around the Mediterranean.
Yeah, and I didn't even get into that part of mineralization because you could also be looking at like basalt and peridotite geologic formations and injecting CO2 into those in situ and storing CO2 that way through mineralization. And my understanding of that is that, well, the mineralization part is definitely permanent. You've like mineralized the CO2 into a solid form, whereas it's not as necessary. It requires more monitoring and verification with the saline aquifer storage. And then as far as picking one over the other, I think it's more of just the question of where is the CO2 that you're capturing and what storage method do you have available nearby? Because it's not all, you don't think you always have the choice depending on what geographic location you're at.
Do you have the same problems with injection with earthquakes that they're having with fracking, taking stuff out?
I'm sorry, could you repeat that?
You know how with fracking that it's creating earthquakes in places because of extracting too much stuff and shaking everything up. With injection, do you have earthquake danger in the opposite direction?
So the injection of CO2 into the salt has been demonstrated pretty well in Iceland with the CarbFix project, and to my knowledge, they've only hit 12,000 tons of CO2 scale, so they're not at large scale yet. But they didn't have any monitoring and stuff, they didn't have any of those type of issues associated with that project.
Sorry to jump in again. I think a lot of the general consensus around that, outside of Carbfix, is that seismicity when it comes to injecting CO2 is not an issue like it is for fracking. They're fairly separate, and I believe models as well as studies have shown that if any seismicity is induced, it's like 0.02 on the Richter scale, which is a pin dropping basically. So it's essentially not an issue, but it's like a kind of like a big risk perception that hasn't been proved true yet through study and modeling.
Mm-hmm. Yeah, it'll be really interesting because I know I read that like the Iceland government now has like signed, I believe signed a thing to allow this Carbfix to be implemented at all of their geothermal plants. So as the scale increases, we'll see what happens. But yeah, so far so good, it appears.
Hey, Caleb, I had a question.
Yes.
I've read some stuff before about being able to create H2 as like a byproduct of this process through electrolysis, but I'm myself very unfamiliar with that process. Do you know anything about that? Is it actually viable?
Yeah, I think I just read about that from like Grishma Gadakota. Yeah, so she said that because with producing hydrogen, you have the water gas shift reaction that produces CO2 as a byproduct. So if you're taking that CO2 and then using it for mineralization, that's actually, that would like Le Chatelier's principle, that would drive that hydrogen reaction towards the products and create more hydrogen. So yeah, I am familiar with the concept and it sounds really cool. And then I think you could maybe use the hydrogen to be helping like power the mineralization. And from what I know, I know that paper was like this year or at the end of 2019. So I think it's a pretty new concept. That it's a really cool idea.
Yeah, it was just something that I've been trying to find out more about, but it doesn't sound like a lot of people have tried it yet or done anything with it. So I was just wondering if you even like,
Yeah, I think it's
knew
very,
what the process
very much
was like.
Yeah, I mean, the main thing I got from it was just like the basic of how it would work and how by using the CO2 that's co-produced in the hydrogen production, you would actually be promoting more hydrogen production. So yeah, it's a really interesting concept, but I think maybe Grishma Gadakota is just working on it on her own right now, from as far as I could tell. So maybe it'll catch on.
Yeah, it could be cool. Could be another
Yeah.
good product to make from this. I don't know.
Yeah, definitely.
I'm curious, Caleb, about feldspar. It sounds like that's something that you're thinking a lot about now and how to make it be more effective. What are your early theories on that, and what might you need to do to make feldspar be effective for removal?
So I'm looking at I mentioned like the common additives for this extraction is using like ammonium salts, and one that's pretty popular in the literature is ammonium sulfate. However, that doesn't work well for calcium silicates like our anorthite, the feldspar, because it produces calcium sulfate that is insoluble in water, and you can't really get it to react with CO2 as well. Anyway, so the plan is to be looking at alternative ammonium salts like ammonium chloride or ammonium acetate, and also we're planning on testing different weaker acids, and the idea is just based on a literature review where I was able to find like old papers where they were just investigating different dissolution kinetics of different minerals, and they found that like oxalate acid and citric acid are able to effectively dissolve feldspars. And of course, you could be using the strong acids; those work for everything, but those are those that have come with harms and also like increased capital costs because of how corrosive they are. So we want to avoid using that. But yeah, that's actually, I mean, we actually got, my lab mate and I like got a proposal that we wrote last fall to do this. So that's what we're planning. We're supposed to be doing it right now actually, but it's not happening. So with the thing, so as soon as the quarantine's over, that's the plan, to be trying this out.
If you were to do something with feldspar, would you be able to keep the glittery effect and make it a building product?
As far as the aesthetic appearance, no. I mean, I'm not exactly sure what it would. Oh, yeah, I guess I know what carbonates look like. They're usually white, so I know I don't think it would be like the pretty part of that feldspar had initially. Top down also.
Caleb, what are some of the mining costs of some of these materials? I think like olivine can go for like $7.30 a ton or so, and I think it depends on how close you are to a site, what the mine is, what country it's in, if there's mine tailings. But like, have you found like any average figures for mining costs?
Yeah, some of the one of the like top guys in this area, Peter Kelman, in this National Academy of Sciences negative emissions technologies report last year, he put out, he estimates that it's about $10 per ton of rock in general for mining, and then size reduction. Yeah. Subat asked about the open source doing top down. I guess I went through the top down versus bottom up model just as a way to say like that it's more easy, so you can directly say how much CO2 you want to capture for the process, and then based on that, know how much materials are all required. So I mean, as far as changing it to the top down, I mean, I could do that. That's actually what I initially did in the Excel, and then just had to flip it all back when the guys told me that they preferred the other way. So yeah, I mean, we could do that. However, the way I have it right now, it does output the amount of materials necessary for the process. So I'm not sure if it would really add an advantage.
All right. Sounds like maybe questions are tapering off. Does anyone have any other burning questions for Caleb while we have him here? Cool. All right. Well, I was planning to try out breakout groups at the end here, but we've come up close on the end time, which we had as 7:15. So I'm curious, for the folks who are still here, do people want to break out into smaller groups and talk in smaller groups, or do folks have stuff that they need to do?
I mean, speaking for myself, I'm equal with that. I have to go, my class isn't that important tonight, so it's a bit more valuable for me.
Cool. Okay, sounds good. So yeah, we can take a minute, and anyone who needs to run can run. And if people want to stick around, we can break out into some smaller groups and have a conversation. I saw Subat also said that, asked if the PowerPoint is going to be posted. Yeah, Caleb mentioned that he would be happy to share the PowerPoint. So I'll share that out afterwards. Meetup can be kind of weird about how it sends emails, but I'm going to share that. I'll share that on a Google Drive document and then post that on the Meetup page.
Yeah, sounds good with me. The like model that I created and the direct air capture model that my colleague created, those are also available online for download, and I can put that if anyone's interested in looking.
Yeah, those are really cool and worth taking a look at. I saw them on the Prime website.
The public models.
I'm sorry.
Those are public models.
Yes.
Oh, cool.
Caleb,
Yeah,
did
we
you
made
say
one.
the Python project was open source?
Yeah, that's the goal, to make it open source in Python model. And yeah, that's kind of like at its infancy. We're like just had a meeting on how we're going to be doing that, and kind of starting soon since we have this extra time with the quarantine. So yeah.
Cool, very cool. I just thought it was a really cool idea. That's all.
Mm-hmm. Yeah, thanks.
Cool. All right. Well, we're a pretty small group actually now, but we could still, maybe we could break out into 2 groups and chat if you all want to do that. Cool. And Caleb, if you need to go or anything too, feel free. We don't need to force you to stay past the time.
I'm happy to talk and see what's going on.
Cool. All right. I'm going to push the create breakout rooms button and see what happens here. All right. I think you all just got invited.
Oh, I think I have to hit something. It says join.